Today we are going to calculate the base shear forces for a frame of a two-story building using response spectrum analysis and then compare the results with that obtained from Etabs software. Our frame is as shown in the figure, which is a special moment frame. The height of the building, the moment of inertia for the columns, and the weight to be considered in the analysis is as shown. When performing dynamic analysis, such as response spectrum analysis, it's often assumed that the mass of the structure can be lumped at the floors or specific levels. This assumption allows us to analyze the structure's vibration mode easily. Lump mass refers to the simplification where the mass of the structure, including the mass of the beams, columns, and floors, is concentrated at specific points, typically at the joints or nodes of the structure. To keep the explanation simple, infinitely large values are assumed for the flexural stiffness of the beams and the axial stiffness of the columns. Thus, lateral deflection of the frame results from column flexuron only, which with this assumption, the structure's deformation primarily depends on the movement of the land mass at the joints. Thus, further simplifies the analysis as we are mainly concerned with how these land masses move under dynamic loads rather than how individual elements deforms. In a two-story building, there are typically two primary mode shapes when performing modal analysis. In order to calculate the modal base shears, the time period for mode 1 and mode 2 should be calculated. The steps of the procedure is as shown. Once we obtain the time periods, the design response spectrum curve will be used to obtain the design spectral response accelerations. To determine the nature frequencies and thus the time periods, we will solve the eigenvalue problem, which is derived from the equation of motion in free vibration without damping. Mass matrix describes the mass distribution. Stiffness matrix K describes the structural stiffness. The time period T corresponding to each natural frequency W is given by. Now we will form the mass matrix and the stiffness matrix. The mass for each story can be calculated as shown. The stiffness K for each column is given by. For a two-story structure, the mass matrix M and the stiffness matrix K are. The natural frequencies can be found by solving the eigenvalue problem. Performing this calculation will give us the natural frequency and time period as shown. Substitute the natural frequencies back into the first or second equations to obtain the mode shapes. Now we will move to the Etabs to calculate the natural frequency and the time periods. Here we can see that the results are very close to each other. In hand calculation, the calculations are done with a certain degree of rounding, which can lead to some inaccuracies. But Etab used a high precision numerical methods to solve the eigenvalue problem, which provide more accurate results. In the next part, we will calculate the base shear forces using response spectrum analysis.